All right. So, welcome everyone to our second online colloquium for the spring term. Our speaker today is Professor Roger Melko. Professor Melko is the Canada Research Chair in Computational Quantum Many-Body Physics at the University of Waterloo, and he's an associate faculty at the Perimeter Institute for Theoretical Physics. He's one of the leaders of PICL, which is the Perimeter Institute Quantum Intelligence Lab. He's also a faculty affiliate at the Vector Institute for Artificial Intelligence and a chief scientist at the Quantum Stream of Creative Destruction Labs, which is a technology incubator. He got his PhD from the University of California, Santa Barbara in 2005 and was a Wigner Fellow at Oak Ridge for a couple of years. His research focuses on developing computational tools to study theoretical many-body quantum physics, and he's going to tell us more about using machine learning to study these problems today. Roger.
Great. Thanks, Saker. That's a very.
Oh, you're.
Okay. Sorry, I'm back. I said I was muted there. Thanks for the introduction. Great to be here. Definitely, Saker, interrupt me if with a wave if there's any technical difficulties. Thanks, for going through all my many affiliations. I think kind of my main two affiliations are with the University of Waterloo and Perimeter, and what we've done, as Saker mentioned, is to kind of spin out an artificial intelligence lab. It's an AI lab. We call Perimeter Institute Quantum Intelligence Lab, or PICL. The photo I have here is sort of a snapshot of us last summer. We were growing upwards of 25 people who are coming out of the lab, or our resident scientists at the lab. And what we're really doing is studying condensed matter physics, quantum information physics, both using artificial intelligence tools, but we're also trying to contribute technology back into the field of machine learning and so on. So I'll talk a little bit about that, I think, as we go on. So, but first off, we're all physicists, I imagine. At least I'm a physicist. And I got interested, and many of my students and postdocs got interested in sort of artificial intelligence and machine learning, not that long ago. But I like to remind all of our sort of collaborators and colleagues that sort of research on AI, even though it's very popular now, is really an old field. It's as old as the digital computer. The kind of advent of digital computers during and after the war really sparked a lot of, I think, imagination in what we now call artificial intelligence. So Alan Turing's a famous example. If you ever, read his writings, you'll find a lot of sort of references to the ideas of artificial intelligence. And one thing which really stuck with me from Turing is the idea that he believed in order to create, an intelligent machine, you had to start with something like a childlike machine. So, and you take that child and you develop it, into a full-fledged intelligent machine in the way that we've learned from raising humans. Von Neumann, who's pictured in the middle here, who also was responsible for a lot of the sort of hardware innovations, the sort of architectures we use. He was no slouch in the field of complexity, and he really brought this idea of sort of complexity and computational complexity into the field of artificial intelligence. He really believed that in order to tackle complex, I guess, tasks, a good model for this would be, the only model that we really had back in the 40s and 50s. And that was sort of, the idea of human or animal brains. So from these two, you already get the ideas of like learning, like teaching, training a child machine, and the idea of sort of neural networks, or these sort of regular networks, which are in essence the main two ingredients of sort of artificial intelligence today. I'll talk more about specific architectures, but I find this sort of plot also interesting when we think about the history of artificial intelligence. So to a physicist, this isn't, very, I'm going to say, quantitative, but it really maps the idea of sort of booms and busts in the cycle of, let's call it, funding for artificial intelligence. So Alan Turing, again, basically after the war, writing a letter, I believe it was to the London Times, which you can find online, which really spoke of the promise of artificial intelligence. This line is meant to talk about, meant to represent sort of the increase in funding and interest in artificial intelligence as a field. There's a famous workshop, of course, associated with AI at Dartmouth. IPTO is like a sort of an Army research, US was like an ARPA program, I guess is sort of what it would be called now, which really led to a plateau or a really strong interest in artificial intelligence. And then, like we all suffer from at some point, a bad referee report came out on the state of the field and really collapsed, in the late 70s funding. This is one of the big AI winters, if you've ever heard that word, artificial intelligence winter, when there wasn't a lot of funding, wasn't a lot of action. Fifth generation refers to the Japanese, in large part, who picked this up. I'm old enough or young enough, whatever, to remember sort of this AI winter, which happened in the mid 90s and so on. The idea of neural networks, people who were working on neural networks were really, I would say, not in the mainstream sort of during this AI winter. And things started to pick up again. The bubble, with the .com bubble, which burst. I actually added these lines here. Canadian Institute for Advanced Research, because if I didn't mention it, I'm in Canada. It's snowing outside my window, by the way. Canadian Institute for Advanced Research had an AI program, which made a big impact starting in 2004. And I added this, the exponential explosion, which I kind of argue began in 2012. So this 2 points on here that I want to mention again. So the CFAR program, which was led by 3 gentlemen who were called the fathers of deep learning. That's Jeff Hinton, Yoshua Bengio, Yann LeCun. So Jeff Hinton's my boss at the Vector Institute for Artificial Intelligence in Toronto. He's also affiliated with Google. And so one of the ideas of this institute was to kind of bring Jeff Hinton back to Canada. Yoshua Bengio's in University of Montreal, and Yann LeCun's at NYU in Facebook AI research. But the 3 of them were sort of the architects of this CFAR program, the Canadian Institute for Advanced Research program, which was founded in 2004. So very recently, last year, they were awarded this AM Turing Award. If you haven't heard of it, most people call it the Nobel Prize of CS. And really it was for major breakthroughs in artificial intelligence. These breakthroughs are things that were sort of happening all through this time period. I mean, these guys and other people were definitely working on neural networks and AI during these winters, at least the winter in the 90s. 2012 stands out because in 2012, there was a convolutional neural network. It was kind of the first example of deep learning that really blew away some of the benchmark, if you will, the standard data set benchmarks. So they call this the Olympics of computer vision. Oops. But really what the ImageNet classification contest was images like these on the right, attempting to be classified by artificial neural networks. And 2012 marked a huge jump with this paper that I have on the bottom, ImageNet classification with the deep convolutional network out of Hinton's group. This might be a little old, actually. I'm sure it's cited over 50,000 times now since 2012. So that's really the start of sort of what we now consider sort of the deep learning revolution or deep learning phase of sort of artificial intelligence. And those are enviable citation numbers. So now I've said a bunch of things about AI. It's kind of a historical context, but I want to step back and just, I've thrown out words like deep learning, neural networks, just to sort of frame, I think, our thinking or our discussion. I like to think of kind of the hierarchy of all of these words that I've been saying like this. Artificial intelligence is what you kind of imagine it to be, computer vision, natural language processing, things like that, robotics, self-driving cars. Within AI, sort of this big general field that is defined in many different ways. Machine learning is a set of algorithms, and I'm really going to focus on machine learning and some concepts of neural networks. Machine learning is really just a paradigm that, machines learn and adapt from data, kind of like Turing's child machine. You build some rudimentary algorithm, if you will, that can adapt to data that it's being exposed to. Neural networks refer to kind of an architecture and maybe a training paradigm. And I'll go through like a sort of basic neural network in detail. Deep learning, I would essentially say, is a subset of neural networks. So deep learning, which I'll maybe show some schematic examples of, is just the idea of maybe stacking many layers of these neural networks. I'll get to all of these. Sekar, I don't know how we want to handle questions. I can pause if there's anything that's come up now, or I can keep going.
So the recommendation right now is that if you have a question, please put it into the Q&A in the Zoom window, and it'll pop up on my screen. And if it's appropriate, I'll interrupt you, Roger, with the question. Otherwise, we'll have the more extended Q&A at the end.
Excellent. It's always appropriate to interrupt me. So let me take this and now turn to physics. And this idea of machine learning, which I mentioned, the idea that, we have kind of a data-driven approach. It is new in the sense that we don't often think of algorithmic design within physics, the algorithm itself as sort of a data-driven thing. So, the basic concept of machine learning, or the paradigm, is really what I wrote here. Instead of designing an algorithm to be completely somehow deterministic, and I'm looking at, say, here's a neutron scattering pattern. Of course, we all have our own data sets that we can imagine in physics. Here's configurations of an Ising model. This is some STM image. This is some quantum gas microscope, individual atoms fluorescing. The kind of idea behind machine learning is to take this data, your favorite data set, and to make it so that the program itself is adapted by that data. So we program these computers with the ability to learn and to change based on the exposure to data. And within machine learning, there's sort of three broad, I would say, subfields that are defined that I've listed here: supervised, unsupervised, and reinforcement learning. So supervised is kind of the most familiar one to most of us. Not me personally, but those of us on Facebook. I see through my wife's Facebook, the idea that you can tag people with their names. Those names are labels. So supervised learning is data with labels. When you, click on somebody's face or image and you type their name in, what you're doing is you're supervising the learning of Facebook's massive AI algorithms to attach that label to other images. Okay, that label doesn't have to be a name; it could be a characteristic. If you go on Amazon Web Services, you can fool around with their image recognition program, upload your images. It's kind of fun. I took a picture myself. It identifies my age. Am I smiling? It tries to guess your mood. You can immediately see how these labels become very sort of powerful things when associated with data. So the domain of supervised learning is this idea of attaching labels and training with labels. And we'll go into that in detail. The vast majority of data kind of out there in the world is unlabeled. There's no human supervision to tell you, or to tell, the computer what you want that label to be. And so unsupervised learning is very broad. It's still data driven. It assumes that you have data, say neutron scattering data or something like that. But you're looking for maybe not specific labels, or maybe you don't know the labels. So you're looking for underlying structure. Clusters, you would love to have an unsupervised learning program that took all of your cat and dog pictures off of your hard drive and separated them into cats and dogs without any supervision. That's kind of the point of unsupervised learning. I'm going to use unsupervised learning in the last half of the talk to learn an underlying distribution. So that's called generative modeling, and it's a little different than kind of just classifying images. So unsupervised learning is sort of a big domain. Reinforcement learning, the last one, I won't talk about, but it's also something we research in physics, especially in control theory and quantum control and things like that. Quantum error correction is another example. Reinforcement learning is the concept behind sort of self-driving cars, a lot of gameplay, you know, these like computer programs that can beat Go. There's no data sets, so they're not scraping the internet for data. What reinforcement learning is doing is taking input of, they typically call it the state of an environment. So imagine a self-driving car, the environment's the road, the state is where it is on the road and what's in front of it and behind it. And the actions are like gas, brake, turn left, turn right, things like that. So what reinforcement does is take in all of these kind of as input, the state of the environment, and proposes an action based on a policy. So you're trying to optimize what they call a policy with reinforcement learning. And it's really, again, robotics, self-driving cars, gameplay. It's sort of a separate field. So supervised, unsupervised, and reinforcement. Let me start with supervised learning. And I'm a condensed matter physicist. I work in statistical mechanics. So I'm going to try to frame this in the way that I understand it. And that's by combining sort of two paradigms. One, this so-called supervised learning data set that we call MNIST, and the second one will be the Ising model. So supervised learning. MNIST is a data set of handwritten digits. Okay, so this is in the field of machine learning. There's sort of standard data sets that are used for benchmarks. So if you come up with a different machine learning, neural network or a paradigm or a algorithm or a method, what you typically do is you benchmark its performance on standard data sets. And MNIST is the most standard of all standard data sets. It's 70,000 images, which are handwritten digits, like 0 to 9, and they were handwritten by US Census Bureau employees and high school students, I believe. Okay, so each image has a label associated with it. So here you see, here's a 5. That's a 28 by 28, say grayscale pixelated 5 that somebody wrote by hand. And the label associated with that file is 5. So the label is the expectation of what that digit is. So I'm going to show you how to perform supervised learning on MNIST. And I want you to think of sort of the most basic model of statistical physics, which is the Ising model. So this is how we're going to ground ourselves in physics by, instead of thinking of handwritten digits, think of the equivalent, 28 by 28, two-dimensional Ising model state configuration. Could be ferromagnetic up, ferromagnetic down, critical, disordered, and we're going to think about how do we attach labels like that. So back to MNIST, the strategy for supervised learning is really to find the function that maps all those pixels, right? Those 28 by 28, which is, I guess, 784 pixels, to the label. Okay, so the sort of input vector, if you will, is just the vector of all these grayscale, or let's imagine they're black and white. So then they're binary, zeros or ones. So you get a whole bunch of zeros and ones. And you want the function that takes all of those zeros and ones and says, this is a label out of the 10 possible labels, Y. And kind of the broad, if you will, overview of how that works. The main strategy for that in machine learning is to use what's called a neural network. And a neural network, which I'll go through in detail, is really, you should think of it as taking the pixels of the image, feeding them as input, and then allowing a signal to propagate to an output, which labels, in principle, there should be 10 here. But through all these labels, the output tells you, okay, that input, that set of input pixels really represents the label 5. So there's lots of lines and circles. There's pixels coming in. There's what I'm calling activation functions here, and there's all these connections. So let's describe those in detail. So first off, the activation functions of a neural network are really gatekeepers that let signals propagate. So here I've zoomed in on one. So here's my input vector. It could be black and white pixels. These X's could be zeros or ones, or they could be the output of another, a deeper layer of the neural network if you have a deep neural network. And each one of the lines on the previous diagram are what's called weights. So we have an input vector, we have weights that I've labeled ij associated with this activation function or this neuron I. And each I also has a bias. What are all these weights and biases? They're typically used to determine the output of this activation function. So the output is given by some function, and I've given 4 examples of common functions in machine learning. So my favorite is a sigmoid. I don't know why. Here's a sigmoid function. It takes the input vector x, okay, and outputs this function 1 over 1 plus e to the minus sum over j weight ij xj minus the bias. Okay, so here I've just taken the argument, called that z, and here's what a sigmoid looks like. So its output goes between 0 and 1. Okay, so this signal that's fed to the next layer, or fed as the output of the neural network, is really just the output of this function. And these functions have to have all sorts of properties that, they're differentiable is kind of the important one. The gradients don't vanish and things like that. And at the bottom, there's other options for these functions. Originally, many people use just a step function. They call it the perceptron. That has some gradient problem you might imagine in the middle here. Hyperbolic tangent, basically the same as a sigmoid. This function here on the lower right is a rectified linear unit. This one actually performs very well. And when you look at these, you start to get an idea for what goes into the art that is the state of the art, which is a lot of heuristic, I would say, engineering design. We don't really have a sort of strong, I would say, first principles reason for using something like a rectified linear unit over a sigmoid. Typically what happens is people discover that one of these performs better than the other, and it gets adopted into the toolbox. I'll come back to that in a bit. So let me take all of these activation functions and just write down the simplest, what they call feed forward neural network that we can construct with this paradigm. So now the input layer, I've just made it square so that we are thinking about grayscale or black and white pixels. Okay, pixels I've stripped out of the image, zeros or ones. I have a hidden layer of activation functions connected by weights, and then I have an output layer, and this output layer is fixed to the number of labels I have. So in this case, for MNIST, it would be 10. The hidden layer can be varied. The size of it can be varied. So the input layer has to be this number of pixels. The output has to be the number of labels. But the so-called hidden or latent space is something we can vary, which we call a hyperparameter to distinguish from the weights and biases, which are the parameters. So incidentally, so these weights, blue weights and biases, are the things that are learned, right? So when I do machine learning, what I'm doing is I'm adjusting these parameters, okay? Something like the number of hidden layers, the hidden units in the center layer, or the architecture of the neural network is not adjusted during training. Okay, say that on the next slide. So what learning is using the data, it is data-driven, to assign the weights and biases in this case, or what we might more generally call the parameters of the neural network, okay? And the way this is done is by essentially feeding in all of that data that you have and deciding, if you will, how to update the weights and biases based on every single data vector that comes in. So typically on a data set like MNIST, it's split up into training and testing, or they might call it training and validation images. So for example, I could use 60,000 of the 70,000 images to feed into the left side of the neural network and to train the weights and biases. And then I can use 10,000 to test whether or not that training was successful. So that's a typical kind of training testing paradigm in machine learning. But how do I update the weights and biases? So we need to define this procedure for learning, you know, the weights and biases based on the data. And to do that, we need a cost function. When there's an output here, we have to know whether or not that output is good or bad for every single instance of training. So here's that output layer. Here I've defined a cost function, just the definition. So, you know, this is a sum over all elements in the training set. So maybe it's 60,000 MNIST images. And this is sort of a simple mean square error. It's just the expected output from the labels, which are a priori labeled, minus the actual output that comes out of the neural network, right? So when they're the same, you get zero, your cost is zero. There's a minimum to this cost function. There's a global minimum, if you will, to this cost function. And that's kind of the right language to think about. What neural networks have done is they've cast this problem of labeling data as an optimization problem. And this cost function really defines the landscape. And what you're doing when you have an untrained or a randomly initialized neural network is you're sitting somewhere out in the rhubarb here, you know, in the cost function. And then as you minimize this this cost function, you're adjusting the parameters to hopefully fall, you know, somewhere towards this global minimum. And what's kind of remarkable about machine learning with neural networks and so on is that a simple gradient descent is used to kind of traverse this optimization landscape. So in physics, we sometimes use much more sophisticated kind of optimizers or optimization techniques. But in machine learning, it's really just the idea of calculating the gradient of the cost function, okay? And updating the parameters. So I'm calling them lambda, just it's all the weights and biases, just updating those based on that simple gradient descent algorithm. So the so-called learning rate that occurs when you think about gradient descent is another hyperparameter, like the number of hidden units in the neural network. So these hyperparameters are things that you're not learning per se, but you're adjusting to give you the best possible sort of optimization. And you know, there's not much more to it than that. There's a little bit of sort of secret sauce that goes into you know, the state of the art. The full gradients typically difficult to calculate, so you break it into small mini batches. They're called stochastic gradient descent. It adds some noise to the whole procedure, but in the end, you know, it's sort of the gradient descent piece is sort of, I guess, conceptually simple. I would say, you know, the best way to understand this is to get a feel for it. And the way we all learned was to really just, you know, download one of these kind of really well-developed machine learning, if you will, libraries for Python, like TensorFlow or PyTorch, I would say, and just look at MNIST, build up your first neural network, use a feed-forward neural network, throw in 60,000 training images and test on 10,000 to see what percentage are classified in error. And with a simple one-layer feed-forward neural network like I showed, with 100 hidden units, you'll basically get about a 2% error in classification, which is, it's 98% accurate. It's actually remarkable. You know, if you think to where we were in digit type recognition algorithms even a decade ago, it's amazing. The state of the art is actually, you know, 0.2% classification and error. So again, this data set like MNIST, CFAR10, ImageNet, all of these standard data sets are really used to benchmark methods. And this is kind of state of the art as of, I think, as of now, came out in 2013. 0.2%, keep in mind, at the bottom here, you'll see what some of these US Census Bureau workers and high school students think pass as numbers, and they're really crazy. So these things are basically unclassifiable, and that probably makes up a large portion of what's going on here. So I you know, recommend trying it. We tried it, you know, back in probably late 2016. And what Juan Carrasquilla did, who's my collaborator at Vector now, is really said, you know, we can really turn simple MNIST classification, supervised learning into a phase classifier, if you will. And the whole idea is going back to the Ising model, just treat the, pixels of the image as the Ising spins, take a two-dimensional Ising model, strip out, the spin ups and spin downs as a vector, put them through a feed-forward neural network, and then classify. And the classification that makes sense for something like a 2D Ising model at finite temperature would be ferromagnetic or paramagnetic. So Juan produced a training set of different temperatures.
Roger.
Yes.
A question just popped up on my screen. I'm sorry, might be a little bit of a delay.
No problem.
So there's a question about I'm curious about the nature of the classifications. How often do people test against probabilities of classifications rather than with discrete best estimate values?
So what I'm talking about here is a probability, and what's the other option? A discrete
best estimate values.
I guess I have to know. I don't know how that's defined. So best estimate means like the best.
Brian, do you want to type a follow-up? Or I guess, would it be more helpful for me to enable you to talk? Okay, I've allowed you to talk.
Okay, cool. Hi.
All right.
Yeah, so my question is, on this slide, when you're saying the percent classified in error, right? You have 2% of them are classified incorrectly.
Right.
But your neural network would output a probability of it being correct for each one of the 10 digits, right? Or does it only give you, it just says it's just, ultimately it's discrete, it must be 0, 1, 2, 3, whatever.
Right. So there's different ways to set it up, but you can imagine that. So now this thing's trained that I have on the screen here. And you can imagine that you've input, say, the digit 5. And what happens is a signal in principle gets propagated through here, and these neurons will fire. And what will happen is most of the neurons, if you will, output amplitude will be close to 0, right? And then one of them, which hopefully is the label 5, will be higher.
Right.
So, each one of them maybe is just outputting a sigmoid. That's kind of the simplest setting, right? So if the thing's trained well, you basically will get most of them outputting down here, and then the actual label outputting up here. But you basically you look at the neurons in that case and say, which one is the maximal output? And then you choose to assign that label 5, for example, because it can't be more than one label.
Right.
Except maybe if you start looking at some of these, right?
Right.
Well, yeah, so you can look at either way. You can just choose the label as being the one with the highest output, and then run the experiment many times over the 10,000 testing images. And that's kind of how you get these percentages. Or you can look at each individual one and see how exactly the structure of the network fires and so on.
I see. Okay. Okay. And so that would ultimately, because it just occurred to me that if you're wrong, if you're wrong, if you're not as confident that you're right on the ones that you're wrong, if you see what I mean.
Yeah.
If there are ones where your estimate says it's 50% likely to be 2 and 40% likely to be 3, that would be a better outcome than one in which, if the real answer is 3, say, one, then you were definitely 2, 99% 2 and 1% 3. And so
you can have less simple output layers that are actual probabilities, just like that. So they're normalized probabilities. And then, you can actually look at the distributions and so on.
Right. Okay. I guess that's what I was curious about. Thanks.
Yeah, you can definitely do that with these like softmax outputs or something like that.
Sure. Thank you.
Yeah, so absolutely. So now just all I'm saying here, how do you turn this into condensed matter or statistical physics or whatever your field is? Just replace the image with your data. And so here, an interesting label is ferromagnetic or paramagnetic. And the reason I use that is because there's a phase transition in the two-dimensional Ising model around 2.269. Okay, it's not here. But some of these images at the bottom are in a paramagnetic phase, and some of them are in principle in a ferromagnetic phase. So what Juan did was train a bunch of images like this, say 5 or 10,000 at each discrete temperature, and then do a test set that was many different temperatures. And this is the output here. Okay, so here's ferromagnet is blue, paramagnet is red, and here's the average of many of these experiments. So you can see, here's a blue L equals 10, so that's a 10 by 10 lattice. As you get closer to the critical point, which is marked by this line, this orange and blue line, you see that the confidence of that output, or the average of that output, starts to drift away from unity. At some point, it crosses 50%, which is the critical point. And then, the network becomes pretty sure that this thing is in the other label. That label is the red, so the paramagnetic label, and you can see the opposite behavior. So you can study this in detail and even extract, the critical exponents based on the 50% crossing and so on. There's a big rabbit hole you can go down here, and we did. But this really kind of, for me personally, when I saw this result, I was like, okay, now it's really clear how you kind of understand how this supervised paradigm can be used for many different data sets in physics. And let me say one more thing about physics. You typically don't get stuff like this, right? You know what the ground truth is in principle, and you can build models. So we don't have to train a neural network to recognize a ferromagnet from a paramagnet, because you know how to do that with like an order parameter. And so what's nice about physics and statistical physics is really the idea that you can build models of neural networks out of your pre-existing kind of notion of ground truth. So this has become much more sophisticated in the last couple of years. And I'm just putting up two kind of recent examples of people using exactly this paradigm to classify real experimental data sets. So here's BISCO images from Seamus Davis's lab in Cornell, STM images where Frank Zhang, Una Kim, and collaborators basically classified sort of the correlations, the CDW correlations in these images. These at the bottom are also images from quantum gas microscopes, of basically trapped atoms, like ultra cold fermionic atoms that are lithium atoms that are meant to emulate the Hubbard model. And so what this collaboration did is look at these images and try to classify different theoretical categories of correlation functions. So supervised learning is a paradigm, is really just is really close to sort of these ideas of automating discovery and so on, I believe, in data sets.
So
I'll pause there for another round of questions if there are any.
So that assumes, though, that you know the answer in some level to when you're doing the supervised learning. And so when you're looking at correlations or more complex systems, quite often the challenge is that you don't know the answers.
That's exactly right. Like here, these labels, these categories are a priori labels that we have competing theories, we might have hypotheses. And so there's a lot of input that goes into that. Yeah. So that's really just a setting of supervised learning. What you really want to do with this is to evolve it into something like Jan LeCun calls maybe semi-supervised learning, or something more towards unsupervised learning, where you extract unknown correlations and unknown physics from the data. Okay, and I think that's basically where this field's going. So I'm somehow talking slower than usual. So I'm going to go through the second part on unsupervised learning, but I'll skip through some of the details to go a bit faster. So I want to change gears. So this is kind of one example, supervised learning. This is how we're using it. I mean, you can imagine your favorite data set, plugging it into these things, having hypotheses classes, doing stuff like that. We also, in my group, work a lot on an unsupervised learning paradigm that's called generative modeling. So what generative modeling is slightly different. It's really, the idea is to take not a whole bunch of different classes of images, but maybe just one class, like the number 2 in MNIST, and really trying to figure out what makes it tick. And by making it tick, it's like, by, what's the quote? It's like, if you really understand something, you can create it or whatever. Generative modeling, the idea is that you can generate a new two that's a completely synthetic two that comes out of the neural network based on training just from data. Let me make that a little more formal. So imagine I have all of those numbers or some other data. Here's a black box. In it is, I don't know, high school students sitting at a desk writing the number 2. And I don't see in the black box, but all I have really access to is these vectors of data. So maybe it's 780, whatever long, and I might have, say, 10,000, which is a reasonable size of data. Unsupervised learning, one setting for unsupervised learning is really just to build a probabilistic model of what's inside that black box. So I've labeled it P of X. So I'm assuming that there's some probability distribution in there, and that probability distribution produces these samples. And what I want to learn with machine learning and neural networks is parameters, like a parameterized model that represents what's in the black box, the target distribution, as accurately as possible. And so the paradigm I'll use is a neural network of some sort, but really you can see that you don't need the output layer anymore. So you can imagine sort of a 2-layer neural network that has a visible and a hidden layer. And if you trained it, you could sample the visible layer to give you new, sometimes I have a hideous picture of a neural network produced generated cat, but I don't know. The 2 seems more concrete. So this is a sort of really rich playground for ideas in statistical physics too. And let me just kind of mention the, I would say the main paradigm in generative modeling, which is the restricted Boltzmann machine. It actually came from work pioneered by John Hopfield in '82. John's at Princeton. He's a condensed matter theorist. He was Bert Halperin's advisor and maybe Steve Gervin. So, he's basically in the same field as me. And you can see that because his idea for a generative model was really an Ising model, taking an Ising model on an arbitrary graph and learning the interactions. What Hinton and others did was extend this idea to what's now called a restricted Boltzmann machine, or RBM, which looks kind of topologically very similar to that neural network with the output layer cut off. So there's an input layer, that's image pixels, and there's a hidden layer, but instead of activation functions, the hidden layer is just binary variables now. So the hidden layers are just also Ising variables that are 0 or 1. So that's kind of the main difference. There's still weights and biases. So now we have biases on the visible and the hidden. And a restricted Boltzmann machine is very familiar to us as sort of what we call an energy model, because we define an energy, which is like a Hamiltonian, and that, the weights are the Ising interactions between visible and hidden, and then the biases are just fields. So you have interactions in magnetic fields, and we define a probability distribution through the Boltzmann distribution, which is a joint distribution between hidden and visible, and that's it. That's the parameterized model that we would like to learn to represent the target distribution that's in this black box. So that's kind of, again, the simplest setting for unsupervised learning with generative models. It's you're learning these weights and biases so that this P of lambda, which is your approximate parameterized distribution, is as close as possible. Oh, and I've written it here, to the target distribution. And the point is with the hidden units is they're, they can be traced over, or they can be marginalized out to produce the marginal distribution, just P lambda of X. And X is, again, the visible layer. So the goal with generative modeling is to train this marginal distribution to be as close as possible to the target distribution. And to do that, you have to define a cost function, just like we had the mean squared error or whatever it was before. The common cost function for this type of problem is the so-called Kullback-Leibler divergence, which is a kind of relative entropy. So here I've written it as a sort of relative entropy between the target distribution, P, and the P lambda, which is the parameterized distribution I'm trying to learn. And really what this KL divergence does is when the two distributions are the same, it's like log of 0, That's your minimum of your cost function. That's when you have a perfect representation of the underlying distribution. And if there's some difference, then you get some finite value to this cost function. And really, again, the strategy is just to perform gradient descent. So you have to be able to take a gradient of this KL divergence and update the weights and biases of that neural network to try to get these two distributions to lie on top of each other. And there's many algorithms for that, starting with sort of Hinton's work in 2002. These are called generative models because once you learn them, once you learn the weights and biases, you can sample them. Just like I want that new, synthetic image of a 2. So how would you do that? The way you do with the RBM is, well, I won't go into details, but once it's trained, you can basically use a Markov chain to sample, just like a Monte Carlo. Just imagine doing a Monte Carlo method to sample visible and hidden in succession. It's called block-Gibbs sampling. And just like you would in any Monte Carlo method, you can calculate the estimators for observables or expectation values through estimators. And any physical estimator that you can define on the visible units, like an energy, a specific heat, a magnetization, a susceptibility, you can calculate in this way. And so this is sort of a large field of research now where we use, I would say, kind of standard, if you will, models, to overuse that word, or standard paradigms in statistical physics and quantum physics to test how well these different generative models work. So you kind of know ground truths in many cases, like energies, and you could ask how well the physical estimators match exact values, and you can also ask about how the accuracies depend on all these hyperparameters and so on. So a simple example, again, just going back to the 2D Ising model, if I train a generative model on that data set that I showed you before, for instead of predicting ferromagnetic or paramagnetic labels, I could have a whole bunch of different temperatures. I could train a restricted Boltzmann machine. And then once that machine's trained, I can have it produce samples that I then calculate energies and specific heats on. And here you see how the accuracy is affected by the number of hidden units. So the black, which is hard to see here, is I produce samples with Markov chain Monte Carlo on the correct, exact, finite size Ising Hamiltonian. And the black is the exact answer. And then the pink is the generative model, synthetically, or whatever you want to call it, generating samples that apparently don't give me the right energy here when I only have 4 hidden units. But when I go to 16 or eventually 64, I do get the right energy. And here you can see specific heat near the transition, right? You get large discrepancies where there's high fluctuations, which converge. So this shows you that the number of parameters in the neural network, or in the stochastic neural network, or the model, they have to be increased to some point so that they're in the parlance of machine learning expressive enough to sort of represent that underlying distribution. And we can play all sorts of games looking at different architectures of neural networks to see which ones are best for critical systems, what's the minimum number of parameters that typical neural networks need to learn a critical system. And we can also play these games with measurements. How many measurements do I need to accurately reproduce energies, specific heat, magnetizations, and so on? So just with 2 or 3 more slides, sorry, I'm running a little late. Kind of, I think the sort of most interesting direction of research that we use these generative models for now, aren't really necessarily for benchmarking machine learning with known things like the Ising model, but it's really as learning the wave functions of quantum devices and kind of near-term quantum computers. And let me give you a really simple example. So now I want to imagine, instead of learning a probability distribution, I want to learn this something more complicated, which is a wave function. So very similar in many ways, except of course a wave function has complex amplitudes in general. But if I have a real positive wave function, which is, I won't get into it, which is a large class of wave functions associated with so-called stochastic Hamiltonians, so we know examples of these wave functions, then really I can map these two problems to each other just by mapping a probability distribution to psi squared, right? just sort of like measurement statistics that you would get. And so here's a Hamiltonian that falls into the class of, I know that it has a real positive wave function. It's the transverse field Ising model. So what I've done is I've taken a two-dimensional Ising model. I've added a transverse field. So sigma x does not commute with sigma z or sz. But without getting into notions of informational completeness and so on, what I can do is I can produce samples of images, if you will, say from an experiment or from a black box, that are really just Z. Sorry, you're in the States, right? So SZ. So these SZ images can be used to train a neural network and produce estimators, just like I showed here, which I would call diagonal estimators now. Okay, this is the formula to do that. But we also have tricks to look at off-diagonal estimators or off-diagonal expectation values. So here is a plot of the red and blue are sigma z and sigma x magnetizations as a function of transverse field. So as I turn on the transverse field, I destroy the regular ferromagnet and I turn on a paramagnet. And what's kind of remarkable is that even though I've trained the neural network in just the sigma z basis, I get the correct output for the sigma x magnetization because I've really learned the wave function, modulo the, condition on the fact that there's no sign. So red and blue colors are from the restricted Boltzmann machine, and the dashed lines are the exact answer from quantum Monte Carlo or something like that. So I know that this works. We've tested this quite a bit, and now we've turned this towards experiment, and this is what I think is really amazing. So the experiments that have come out of Harvard recently, out of Misha Lukin's lab, are Rydberg atom experiments. So Rydberg atom it's either in its ground state or a highly excited state, and I forget which one's which, but let me assume that the holes in these images, the red holes, are Rydberg states. One of those fluoresces, so you can basically do projective measurements on these Rydberg atoms to tell if they're in the ground state or the Rydberg state, and by adjusting the lattice size, if you will, or spacing, the Rydberg atoms can repel each other. It's like a Rydberg blockade. Think of a Coulomb blockade, but it's this Rydberg blockade. The Hamiltonian that Misha Lukin and collaborators implement in his experiment is essentially a transverse field Ising model. So we know that the wave function, these are real images of this 51 atom quantum simulator. We know that wave function is real and positive. So we can use these techniques to reconstruct the wave function and to give output. And here's, long story short, this is my nice cartoon. Here's stabilizing Rydberg atoms, doing projective measurements, and then attaching a restricted Boltzmann machine to that output to learn the wave function. So it's a type of tomography. It looks good in the picture. In reality, what happens is they just email us the data. But I like to imagine hybridizing AI with a quantum computer. Just like the transverse field Ising model, here's a parameter in the Hamiltonian, delta, some detuning strength that shuts off, if you will, the ferromagnet and turns on some staggered phase, which I've Z2 ordered phase, which I've labeled here. Here we can, exact diagonalization is diagonalizing the Hamiltonian. This is on 8 sites, so we can do that. Experiment is the black line, and the restricted Boltzmann machine is the colors. So we've taken the data, we've trained the RBM, and we've reproduced the output of the experiment. Where this is useful is just like in the previous slide, when I have something that's off diagonal or something that can't easily be measured. So in the Rydberg experiment, again, there's some fluorescence probe, essentially, that tells you if you're in the ground state or the Rydberg state. That's the computational basis, right? That's really just the basis that they have access to in terms of projective measurements. What we can do with the RBM is we can take those projective measurements, learn the wave function, and then calculate off-diagonal quantities that aren't related directly to that basis. You have to do a rotation. So here's the equivalent of this sort of in-plane magnetization in the Rydberg language. And you can see as you turn on this parameter, the experiment, which is reconstructed in the RBM, starts to deviate from the dashed line, which is the expectation of the Hamiltonian. So this is feedback or verification of the experiment. It's a characterization and verification of the experiment, which looks like it's working perfectly based on the data that's available. But, you know, through this reconstruction of the state and further probing of different observables, we can help the experimentalists find discrepancies in their setup.
Quick question, Roger.
Yep.
How do you know that it's a problem with the experiment and not with the RBM?
Great question. The short answer is you don't. Okay. And it's a question of how well do you know anything about your training, right? So the RBM, you have a Kullback-Leibler divergence, you've done some training, you hope everything works, right? But maybe you're down in some local minimum, things like that. Like there's the idea of verification of training is as difficult as sort of the quantum verification problem. So that's kind of a deep question that I don't have a good answer for. But my sort of my cop-out is to just say that we can probe many different types of observables, and this is very common, I'd say, in sort of condensed matter. Is sort of you look at different, you know, phenomena that are coming out in measurements, and you basically just try to understand what's going on. If you think about it as a state tomography method, really what you're lacking here is some sort of certification. I think is the proper word, like a formal certification. So that's difficult.
Thank you.
Just to say, like, for example, we can measure entanglement entropy, which I won't tell you how we do it, but so that's entanglement entropy here is different. Here's a chain of Rydberg atoms bipartitioned into different bipartitions. Here's the reconstruction of the entanglement entropy compared to the what is the target entanglement entropy. These types of things help quite a bit with the experimentalist trying to verify what's going on, because the entanglement entropy is basis independent, right? And so it's just another probe. I would say in the condensed matter sense, it's just another probe into these many body systems. They give us a lot of clues into what's working and what's not working. And by the way, this kind of probe of the entanglement entropy, although it can be done with our reconstruction, before that was done with some massive experiment where physical replications of the state had to occur and so on. So one of the points of this is that we're replacing a massive experiment with, email me the data type of thing. So just to summarize, generative modeling, the last part of my talk, is really making it possible to take the data from experiments and to view it in different ways, right? I only talked about the real positive wave function, but
Roger, we have another question.
Okay.
Oh, actually, we'll come back to that at the end. So I just so you know.
I only got 2 slides, so.
Yep, go ahead.
Yeah, so one thing I glossed over was the structure of the wave function. Like we all know in quantum mechanics, we can have complex amplitudes. But so the majority of what we research now in my group is sort of I would say the efficiency of reconstruction of these complex phases that occur. So we have different neural network based models that represent wave functions and even density matrices. And so we're turning this into much more of a kind of traditional tomography like method. And the idea is that hopefully this thing will scale well so that, we can do 50, 100, maybe hundreds of atoms if the wave function can be assumed a priori to have no sign structure. The question is, how big can we go if we have some sort of amplitudes and phases? But the takeaway from this is really, we can do the measurements, all the difficult experimental measurements in the kind of synthetic reconstructed neural network, which should offload a lot of the experimental difficulty with complicated measurements like this. So it's kind of a way of augmenting the experiment so that we can get more out of it with less experimental effort. And I'll just end by putting up sort of what I think are interesting questions. I think this question of how do we verify what's going on is fundamental. And to understand whether or not the neural network works or whether or not it learns the wave function, we really have to understand, the structure of neural networks, which ones give you efficient representations, which ones don't. We have to understand whether or not, there's polynomial or exponential resources in many steps. And it's not just number of parameters. It's also in maybe the number of steps to find the global minimum. So now we talk about differences in the landscapes. So loss functions, whether or not they're glassy, whether or not they're convex. All of these things are open questions in most of the kind of machine learning paradigms that we use. But I think kind of the ultimate goal is just really, I'm a condensed matter theorist. My supervisor is Doug Scalapino in Santa Barbara. He, his holy grail, and many of our holy grails was, solving high TC superconductivity. That was understood to be hard. So what people have done is built Hubbard models, like Marcus Greiner has built Hubbard models as highly controlled atomic systems. And so now the question is, can we leverage those atomic systems and can we bootstrap them into with greater and greater sort of power by attaching neural networks to them in this way? And so the ultimate goal is to sort of make progress on some of these holy grails, I think, with this hybridized approach. Okay, thank you very much.
Thank you very much, Roger. So that virtual applause here.
I can hear it
from everyone
washing over me.
Right. So we have one question. So are there machine learning tools for recognizing, learning, or parameterizing distributed data sets, such as vector field maps? So right now, the examples you've done primarily involve scalar labels. So 2 or paramagnetic, ferromagnetic, that's just a binary choice in some sense.
Yep.
Now, and what tools or metrics are being used in machine learning to recognize and parameterize maps of information?
So I don't know any off the top of my head. So we typically deal with, and I think we're talking about labels. So if we're talking about input to the neural network, you can definitely use continuous, like I've talked about binary and I've kind of mentioned grayscales. On that end of things, you could definitely input higher symmetry, if you will, local Hilbert spaces. Absolutely. You can do, we've done things like XY model inputs, you could have any sort of kind of unit you want there. In terms of the output, so I'm not too familiar with sort of outputting a map, if you will, like that. We mostly kind of have discrete labels, but I wouldn't be surprised that some engineer somewhere has developed that technology. So just to sidestep the question, if you think that there's something like that would be useful for physics, chances are somebody's invented it somewhere in machine learning, industry, and all you have to do is search that out and try to adopt the technology. You'll find that some of these things run right off the shelf.
Christina, I've enabled you to speak if you have a follow-up.
Sure. Yeah, the question is definitely about the output, not the
Okay.
input, for sure. And yeah, it's just my question of the year is what tools are out there. I'm kind of in that search mode. So the sorts of things we're trying to do is recognize auroral images as having, a discrete boundary across them. In your condensed matter, I would picture it as, maybe there would be a fracture across your crystal, and could you learn to recognize that distributed information in some way? And there are lots of tools for parameterizing maps and developing a metric for which portion of the map you're interested in comparing and training on. So I was sort of just fishing to see if you had come across something like that.
Not personally, but yeah, I absolutely believe that, this type of thing either, exists in some sense that could be adapted, or it's something that is completely possible to do. It's interesting that you talk about dislocations or things like that, because what's one interesting direction is sort of topological information, right? So, and it has to do with the scaling of these things. So how do you detect either features that aren't just local, maybe you can think of it like that, and whether or not whether or not the power that we believe a lot of these neural networks has translates into these physics concepts like topology and non-locality. I think there's a lot of work there to be done.
Yeah, you get into some really interesting questions when you start trying to decide what metric you use to decide whether this one is like that one.
Absolutely, absolutely.
Right, and you can have one that's exactly the same, but is 3 pixels off, and your standard metrics just return nothing. And so there is a lot of metrics for maps language out there, and I'm trying to chase down coupling it with the machine learning tools to figure them out. So
Definitely happy to talk more about it offline. Maybe
Yeah.
maybe there's some way we can help.
So we have another question. I'm going to let Rahul ask his question. Rahul,
You hear me?
yep.
Yes.
Oh, great. So I have 2 questions. They're somewhat related. It would seem like the function you start with, for example, let's say you were trying to learn phase and amplitude with a neural network of a quantum wave function.
Mm-hmm.
A spiking neural network that naturally has fine timing as well as mean firing rate may be better suited and more efficient to learning it than, say, a neural network that was just an RBM that essentially had only amplitude information. And the second related question is, if I have an RLU that has a linear part, which allows you to learn when you're doing well, but you're kind of flat when you're not doing well on the minus side,
Mm-hmm.
versus a, sigmoid or a tanh that has a nice linear portion in the center that allows you to learn when you're getting things wrong and right in the center, but you're very flat if you're very wrong or very right. It would seem like there's some data sets where an RLU would do best, and there's some where a tanh or a sigmoid would learn best, depending on whether the problem is distinguishing things that are right and wrong that are very fine versus just getting everything right. So it seems like the question is, what do you start with? A spiking neural network versus a simple Hopfield when you're doing quantum,
Right.
an RLU versus a sigmoid or tanh when you're trying to learn a data set with wrong and right versus all right. How do you answer that question? Or is it an open question, or is there some insight that's come out?
So great question. So like if you we'll do the second part first.
Yeah.
So your question was kind of like, so if you look at it on the right, we have the sigmoid, rectified linear. I mean, yeah, you look at those, which one's better? I don't have a lot of intuition for this. I don't know the story about how people found the rectified linear unit, but I think you're right that, in different cases, different activation functions will definitely behave different, and many will have different properties for different data sets. So I think, this all falls within this this kind of realm of hyperparameters. And once you start thinking about what's a hyperparameter, and you think of number of activation functions, the type of activation functions, the learning rate, all these types of things, you see that hyperparameter space is massive. And so a lot of what people have to do is search, they're like grid searches or some more sophisticated searches of these hyperparameter spaces. And that, that it seems discouraging, but there's also a whole field of of machine learning that has come out of that called meta learning. So I'm just kind of just sidestepping the question, but it's because I'm not sure there is sort of a intuition for, what you start with and what you choose in terms of these activation functions, for example. And I really think that a lot of this just comes down to experience with the type of data sets that you have. We typically start with sigmoid and then move to rectified linear. I think that's kind of a common progression. Regarding the RBM, so there's no phase information exactly. I mean, it's when you look at it, it's just a probability distribution. I kind of ended here with an idea of how we parameterize phases. So one way to do it in the RBM, so now, okay, this used to be X, that should be X, but my sigma is my visible unit. And I can imagine having 2 kind of separate, if you will, RBMs, one that parameterizes the phase and the amplitude, and one that parameterizes the phase. And this is how we do it with RBMs. This is how we capture or reconstruct complex wave functions. This phi here would be like another square root of a p mu or something like that. But so basically you can choose how you would parameterize the phase, if you will, as long as that those parameters can be learned through something like a KL divergence. And what happens in this case is that not only do you need to have the parameters for the phase, but you also need to have data in other bases. So in the RBM, we have a procedure for calculating a Kullback-Leibler divergence separately for every basis. And you have to know what your sort of basis you're in or what the unitary rotation is that got you that basis. And in that case, you can learn the amplitude and the phase. Do we start with RBMs all the time? They're not the best or most efficient generative model by any means. We've spent a lot of time on them, us as physicists, because we understand them very well, I think. I believe, I mean, that's why I do it. When I look at this is an Ising model to me. You know, I know exactly what I'm looking at here. But there's features of this that aren't as favorable for things like learning wave functions. And we've actually adopted a lot of different other generative models. So one which I really like is a recurrent neural network, which is used in natural language processing. So an RNN is like a sequence mapping. The input of each node, and I don't have a picture of it here, I don't think, no. But it's sort of the state of a qubit, and that's like a word, and you string together these words into sentences. So, you know, these models are very efficient. They're called autoregressive. They give you normalized probability distributions, which you can imagine is a huge advantage. And really, I think the future of this type of tomography, it really doesn't lie in the RBM. These things are great for understanding kind of the data-driven setting, if you will. But more modern technologies like RNNs or transformers, these autoregressive models will definitely be what's kind of implemented in more large-scale experiments. And this is wide open. I mean, this field of research, you know, looking at generative models for tomography, I mean, it's wide open. There's all sorts of different architectures out there in the machine learning literature, just waiting to be kind of, I guess, explored.
Thank you, Roger. I think we need to close the main colloquium right now. And again, thank you very much for everyone who was here. We have a post-colloquium virtual coffee hour, and you must have received the link before with the password for another Zoom meeting. If you haven't, it's in the chat session right now, and you can access it. But thank you very much for a wonderful colloquium.
Excellent. Thank you.